When you hear somebody talking about waves, you likely think of a simple greeting or the ocean crashing against the beach. But the unique behavior of waves is used throughout large swaths of modern life, and understanding them can explain some of the magic and mystique of the world we live in. Today, we'll be covering the simple version. Generally, a wave is a means by which energy can get from one point to another. But they're so interesting because they appear throughout so much of our universe. Waves can be used to model the sound you hear, kitchen microwaves, traffic patterns, and so much more. In our daily lives, we most frequently interact with two kinds of waves: mechanical and electromagnetic. Mechanical waves, like sound, seismic, and ocean waves, require a medium to travel through. Conversely, electromagnetic waves do not require a medium to travel through, instead using disturbances in electromagnetic fields to propagate. Examples include light, radio waves, and X-rays. Technically, these three electromagnetic waves are all variations of the same thing, with different frequencies. And we give them different names because they have different uses in modern electronics. Although there are endless examples where waves appear, they can all be described using a sine function, a curve with evenly spaced hills and valleys. This curve is characterized by its amplitude, which controls the height of the peaks and valleys, wavelength, the space between peaks, frequency, the rate at which the peak flips into a valley and back, and phase shift, which can move the wave left and right. This definition may seem a little tedious, but understanding how each parameter affects a wave's shape is important in understanding its behavior. Now that we understand the basic structure of waves, we can tackle how they move through space. In many ways, waves are just a series of disturbances that carry energy. When we whip a rope, the wave may appear to be moving some part of the rope away, but this just isn't the case. Instead, your initial whip sets the beginning of the rope into motion, which tugs on the adjacent little bit of rope. This sets up a series of little tugs on each piece of rope that allows the energy to move through the medium without permanently displacing any particles. But what happens if two waves run into each other? Imagine two identical waves moving towards each other along a rope, and we observe the exact particle where they meet. What do you think will happen? Both waves will tug this particle in the same direction, displacing it even further than either single wave could. On a larger scale, we would see the amplitude of both waves adding together to create a larger wave. This effect is known as constructive interference. What if we repeat this experiment, but now one of the waves is flipped, so its peaks are now valleys? At the point where the waves meet, both waves would tug the particle in opposite directions with the same strength, so the particle would not move. The large-scale effect is called destructive interference, where two waves' amplitudes cancel out to create a new wave with a smaller amplitude. Typically, though, in nature we rarely see two identical waves interfering, meaning that the total interference between the two waves is both constructive and destructive. Even if you haven't noticed it, complex interference patterns are something that most humans worry about at some point in their life, including everyone from professional musicians to physicists studying quantum mechanics. Remember that constructive interference can increase a wave's amplitude, so we can use it to amplify signals we want to send over long distances. This technique is used in radio transmissions, since transmitters often want their signals to be received by people many miles away. By placing radio towers at specific separations from one another, their waves can meet and interfere in a way that will increase the amplitude of the radio wave. Destructive interference also has practical applications. In sound, the volume of the audio is determined by the wave's amplitude. So if a sound wave undergoes destructive interference, its volume decreases. Many types of sound-canceling headphones use this principle. Using a tiny microphone to measure the shape of an incoming wave, the headphone can send out a flipped version of it to cancel out the outside noise. These two examples demonstrate the usefulness of complete constructive or destructive interference, but the more shocking interference applications appear when considering a mix of the two. Anyone who has played an instrument has likely heard about tuning, which is calibrating your instrument to ensure it produces the right pitches when you play it. When two instruments are in tune, their sound waves can constructively interfere to create a louder sound. However, suppose one musician tunes their instrument incorrectly, meaning their notes are slightly higher or lower than they should be. In that case, the sound waves can interfere to cause a periodic decrease in their combined volume. Musicians often call this phenomenon beats, and can distinguish between sounding professional or just good enough. Complex interference patterns also appear in modern physics experiments. If you've ever heard of the double slit experiment, you've likely heard that it proved that light behaves like a wave. By observing light spread out or diffracted by small slits, we observed a series of bright fringes surrounded by dark sections. The bright fringes result from constructive interference, and the dark sections are caused by light waves destructively interfering. This discovery was monumental and reshaped the way we viewed light. We've still only looked at interference between two waves, though. When we consider situations where many waves interfere, can we find any practical applications? The Fourier series is a tool that models any function as an infinite sum of waves, including those with sharp edges or discontinuities. It does this by taking large waves that follow the general shape of a curve and adding smaller waves that adjust the overall shape. For example, if we find the Fourier series of a piano note, we can reconstruct the audio piece by piece. But just understanding that waves can be used to recreate complex shapes sets us up to understand one of modern technology's most important mathematical inventions, the Fourier Transform. This topic could easily take up an entire video, so we'll avoid the specifics of how it works for now. But it's essential to large amounts of modern technology and science. If you've ever asked your phone to identify a song, used image compression, or removed background noise from audio, you've likely used Fourier Transforms. A solid understanding of waves can help you understand the wonders of our modern world. If anything, you should take away that waves can interfere with each other, and by carefully choosing which waves interfere, the shape of any function can be approximated. In a future video, I'll discuss how Fourier transforms work and why they're so important in modern technology. But until then, thank you for watching.